Well, hello everyone. Before we start chapter 2, I just want to review a little bit what we did in chapter 1. So we talked about type hypotheses test, null and alternative hypotheses, and type 1 and type 2 errors. So let me give you a general picture here of type 1 and 2 errors. All right, because what we're going to be doing today is calculating the probability of a type 2 error for a particular null hypothesis. Now, let's review a little bit. So what do we have? What is the null hypothesis? So the null hypothesis, and we call it H naught, is the hypothesis of no effect. What does that mean? For example, if you're trying to see if some treatment worked and you do a randomized experiment and you compare the results to a control group, like we did that first day of class when we talked about some smart drug to improve your test scores, the null would be that the drug didn't work, that there's no difference, that the treatment didn't work, that there's no difference between the exam scores between the two groups. Any difference we see is just due to chance, okay? So we'd set a null hypothesis. We'd say, okay, the difference, what did we say? However, whatever test statistic we decide to choose, for example, would be in this case the average scores between the two groups are the same. So there's no difference in means between the two groups. Okay? Means of their test scores. All right, and then you'd have an alternative hypothesis. And the alternative hypothesis, we label it H with a little a here, is the hypothesis that there is a real effect, that the drug did work, that the difference we see in those test scores reflects a real difference, okay? So that the drug did work. It's greater than 0. This is that there's no difference. The difference is equal to 0. This is that it's greater than 0. Okay, so then what do? We imagine what under the null, when the null is true, you have a distribution of this sample statistic that, because when the null is true, think about it, you're not going to get exactly the same test scores for both groups. There's going to be a distribution. I mean, just by the luck of the draw, one group could score significantly better than the other, even when the drug doesn't work. So we have what's called, so you'd have a distribution of the difference between the two means under the null, and it would resemble, in this case, the normal curve like this. And right in the middle would be our expected value. Right here, we'd think a difference equals 0, right in the middle, so it would be the expected value under the null, right? We'll just say we'll call it the hypothesized value under the null. We'll refer to it that way. And in this case, it would be 0, no difference. But even when that's true, just by the luck of the draw, we could see very strong evidence. I mean, theoretically, we could have, think about putting everybody's test scores into a box. And what I mean is put it into a box, shake them all up, and then draw out half of them. So it's the sampling distribution of the means of the difference between those two groups. And it just by the luck of the draw, you could, I mean, it's possible, very, very small probability of it, but you could draw the top half of the scores. And then, the probability of that is extremely unlikely. So at some point, what we do is we say, okay, we've got the evidence for this. This is evidence for the null being true, that the drug didn't work. And at some point, you say, okay, it's beyond a reasonable doubt. And, we have to make a decision and say, okay, the drug works. So at some point, and we call that our null cutoff. We have to make a decision here, right here, okay? And what that's, you set that probability here. This is the probability that we're wrong, that we say, because under the situation that it didn't work, we're deciding that it did work, okay? We're rejecting this null. And so this is what's called the probability of making a type 1 error, and we set that probability. We say, and typically we set it to be 5% just by convention, okay? So this yellow here, this area under the curve, is equal to the probability of a type 1 error. And we choose that set by alpha, okay? The significance level. All right, and typically chosen to be 5%, but we can choose it to be whatever we want. And it should depend on the circumstances, because we have to think of the consequences of when the alternative is true. Now, the alternative right here is a whole range of alternatives here. But we're going to pick a particular alternative to calculate the cost of making the other type of error when the alternative is true, to not detect it. To not detect the difference is called a type 2 error. So to calculate that, we have to pick a particular alternative. So let's think about our example with let's say it's this group of 300 students in this class, and half of you got the drug and half of you got the placebo. And suppose you think that the drug makes some difference, right? We wouldn't be doing this unless we believe the drug made some difference. And probably we wouldn't be doing, I wouldn't really care about a tiny little difference. I'd probably want to see a difference of a few percentage points at least. Now, let's say I think the drug works pretty well and would improve people's scores by an average of 5 points, at least 5 points. That's what I care about. That's the difference I want to detect. So then I would set if it improved your scores by 20 points, I probably wouldn't, it'd be very obvious, right? If the average on one was like between a 90% for one class and a 70% for the other, one group, and the other group, then I probably wouldn't, it would be very obvious. But maybe 5% wouldn't be that obvious, let's say, a 5-point difference. So let's say I set it at that. So let's say the difference here is equal to 0. The difference in means is 0. And here I'll set my alternative that the difference in means is 5. Okay? 5 points out of 100. Now, so that would be my particular alternative hypothesis, and then I'd have a distribution centered at that, right? And it would probably follow a very similar distribution. So let's look at that. Let's say it does and has it's the same shape, it's just shifted over by 5 points. So we do that. I didn't draw it very well, but you got the idea. Okay, so now as long as you think, okay, we're going to correctly decide for the alternative this percent of the time, and that's called the power of the test, but we're going to incorrectly decide when we choose this cutoff, this decision cutoff right here, this percent of the time. And that percent right here is the probability of our type 2 error. of failing. Look, this isn't the difference we want to detect, and we're going to fail to detect it with this significance test if we put the cut up here this % of the time. So that's what's called the type 2 error. The area of that is the probability of making a type 2 error, and that we calculate that. We have to calculate that for each particular alternative hypothesis, and it's called beta. So what we're going to do today is calculate that probability. Now, of course, this looks quite large, and we'd like both of them smaller. Well, if we want this one smaller, the type 2, we're going to have to, it's a trade-off. We're going to have to move our decision, our cutoff to here, and then the other one's going to get bigger. So we want both of them smaller. And so what we'd really like to do is get a test statistic on that has whose sampling distribution has a smaller error bars. Smaller error bars. And one way we can do that is by increasing the sample size. And that's what we're going to do in the second part of this chapter 2. So that's the preview. So let's just go right to it and to an example and see how let's think about how we would calculate, first of all, the type 2 error. So that's what we're going to do first. All right, so let's go to page 4 in our notebooks. And I drew the same little picture right here. This is page 4 in our notebooks. And here, this is where we're at. Now I want you, and what we're going to do here, basically the way that we're going to calculate the probability of this type 2 error beta, we're going to calculate, you have to calculate beta for a particular hypothesized, for a particular alternative hypothesis. And what we're going to basically do is translate this distance here, which is called the effect size. In our last example, it was that those 5 points, this effect size that we're trying to detect, this difference that we're trying to detect, which is, I should put absolute values here, the size of the effect, right? So we're going to, what we're trying to do is we're going to look at this distance in units, all right, distance in units, and we are going to translate it into a distance in standard units, which is a distance in z-scores. So we've got a distance in units and a distance in z-scores, and how do we always translate from a distance from units to z-scores? Well, we use this conversion factor called the standard error, which is what? This is units in units. This is in z-scores. And a standard error tells you how many actual units that we're measuring in per standard unit. Okay, that's the conversion factor. And so when we're doing this type error in this example, what do we know? Well, we know this. For our past example, this would be 5. And we'd have to figure out the standard error by one of our standard error formulas that we've gone over back in Stat 100. And just to refresh your memory, so this would be, we have to use one of our standard error formulas. And for the average, standard error for an average is equal to the standard deviation of our box model. We'll look at that in the next example. The standard deviation divided by the square root of our sample size. And if it's a percent problem, we're looking at the difference. If we're just looking at percents, then it would be the same exact thing, but we'd have to change this decimal to a percent by multiplying by 100. So I'll put a little percent there. And then if it's the example we just gave, it's a little more complicated. If it's a standard error of the difference, which is what we'd want in the example that I just talked about, what we'd have to do is we'd have to, that's more complicated. We'd have to see, so we could see formula we'll talk about later. On page, I can't remember what it is, but it's in the back of the book, and we're going to talk about it later. But it's more complicated. It's basically combining two standard errors. You'd do this. You'd say the standard error for the treatment group, the standard error for one group, squared, plus the standard error for the other group. So this could be the treatment, and this could be the control, squared. Okay? Whoa, sorry. It's like the Pythagorean theorem. So that's the idea. So we're going to use one of these. For now, we're just going to be using these two formulas. All right? So let's just jump right to an example, and you'll see how we do this. Okay, so let's turn to page 5 here. And here's the example we're going to look at. Okay, I think my 2-year-old granddaughter, Talia, is a gifted statistician, okay? So I'm going to test that claim, and I plan to ask her 100 true-false stats questions, okay? And the null hypothesis is that she's just randomly guessing. Nothing's going on here. The null is that she's just randomly guessing. Okay, so under the null, I'd expect her to be correct about 50% of the time. So that's going to be the expected value under the null, right? Just by the luck of the draw. So let's look at that. So the first thing you want to do is look at the sampling distribution of the test statistic under the null. And the test statistic is the percent she's going to get correct. All right? So under the null, we believe she's going to get 50% correct, just by the luck of the draw. All right? That's when the null is true. Now, of course, that's not going to happen every time, right? She's not going to get exactly 50% correct. Just by the luck of the draw, she's going to do better or worse. So what's the probability that she'll get 60%? That's what I'm interested in here. That's going to be my alternative. What's the percent that she'll get 70, that she'll get 50? How do I know those error bars around 50%? I need to calculate, I need to find my standard error, the error bars around here. All right, I know that it follows the normal distribution because of the central limit theorem. The sampling distribution of the number, we'll go into that. Once we set up a probability model, we can talk about that. But now we need to find the standard error, okay? And this, how to find, so we need to find the standard error. So we need to set up a box model, probability model. And imagine the simplest one would be to set up a box model with, a box model is a box with tickets in it and numbers written on the tickets. So in this case, it translates very easily. Each question she's randomly guessing on. So if she gets it wrong just by the luck of the draw, we'll call it 0. And if she gets it 1, right, we'll call it 1. So that's our box model. And what we want to do is figure out if she draws from here, randomly draws, n equals, that's the sample size, 100 times. We'd expect her to get 50 or 50% right, but give or take what? What's the standard deviation? What's the standard error of that? And the sampling distribution follows the normal curve because the central limit theorem says that the sum of n draws from any box, no matter what the number's on it, the sampling distribution for the sum, and therefore the average and the percent, will look like the normal curve the more draws you have. Okay, so now we know we'd expect that, but we have to figure out the standard error. So we have to find the standard error. Okay, so how do we do that? Well, the standard error is going to be equal to, it's going to depend on two things, and it's the standard error what? For the percentage. We can just, for the percent here, because we're looking at the percent, right? And it depends on two things. It depends on the spread inside the box, the standard deviation, and it also depends on the sample size. But it doesn't, it's actually the square root of the sample size. And that's a very important law in statistics, the square root law, and you can see the proof of that in the back of in the appendix. All right, and you can see that, it depends on the distribution here, the standard deviation. Right now, we've got the biggest spread we can with just zeros and ones. We have 50% zeros and 50% ones. So you can see probably just by looking at it that the standard deviation is going to be a half. But because our average is a half, right? Zero, the average is a half, and zero deviates by a half below, and one deviates by half above the average. So, but in general, how do you find the standard deviation if you just have zeros and ones in a box? Well, I should write that down here. The standard deviation of a 0, 1 box is what? It's the square root of the fraction of the box that has zeros on it, 0.5 times 0.5, which is equal to 0.5. So think about it. If you had 90% ones, it would be a much less uncertainty, right? There'd be a smaller standard deviation. You'd have, because you'd be more sure to get a 1 when you know. And so what would it be then? It would be the square root of 0.1 times 0.9, which would only be 0.3. It would have a smaller spread. If you had all ones, and you got them right 100% of the time, well, there'd be no uncertainty, no standard deviation. All right? So this is, so we got 0.5, and then we have divided by the square root of 100 right here. And that would give us 0.05, but we want a percent. We want to change that to a percent. So we're just going to multiply by 100 because it's a percent. So put that in. So that's times 100, and we get 5%. So that's the standard error, okay? So what does that mean here? So if we were doing it in standard units as z-scores, here's our regular units. If we were doing it in standard units, we'd have 0 in the middle, 1, 2, 3, -1, -2, -3. And now we know where to place, now we know we can translate it into probabilities here of what's the probability she's going to get as high as 60%, which is the alternative, by the way. Here's our alternative hypothesis. Okay, I believe she can answer correctly 60% of the time. So where is where is 60 on here? So let's see. So this is 55, it's 5%. Oh, it's right here, 60. All right, so now, and this of course is 45, 40, and 35. All right, so I look at this and I say, wow, the probability of, it looks like I'm pretty, looks like I'll reject the null. If we do a significance test, I'll be able to reject the null. Especially, but we have to set a null cutoff here. And the typical null cutoff is, we forgot to do that, so we'll set alpha equal to 0.05, which means 5% in the tail. And now, what do I want to do here? What I really want to get to is I want to find the probability of a type 2 error. If the truth is that she really can answer the question 60% of the time, what's the probability that this significance test is not going to detect it? So that is our type 2 error, and that's what we want to do. I forgot to add that, so add that. That's what we're doing here. All right? So, so the first thing is, where are we going to set our null cutoff here? I'm going to set, so alpha, so we want 5% in the tail. Alpha equal to 0.05 means 5% in this tail. Why? Well, because we have the alternative hypothesis here, and here's the alternative, is that the percent, her percent correct is equal to 60%. At least 60%. At least. I'm picking the minimal value that I care about, so it's at least 60%. And it's directional. So that means that I want to set the probability in one tail. Okay? So what am I looking for now? I want to find the z-score. Where do I set that? Okay? So what is that? I want 5% in the tail. So I want that area to be 5%, so I have to use a normal table. So let's go to the back of our books and see what z-score corresponds to that. We have a handy table back here, right here on page 159, and it gives us z-scores according to middle area. So if she's 5% in this tail, that means she has to be 5% in that tail, so I should look up a middle area of 90%. So let me do that, and I get 1.65. Okay, not exactly, but let's just use the closest line in the table here. So that means a z-score of between 1.65 and negative 1.65 has about 90% of the area, and that means this would be 5%. So, okay, so we get, so let's mark that. This is 1 and that's 2. So this is going to be our cutoff right here at, we'll call it z alpha, a critical value of z. That's how people describe it. It's the critical value to reject the null. So z alpha is going to be 1.65, and that means this is going to be 5%. All right. So it looks like, okay, great. I believe the true value is here. And so this significance test, I feel pretty safe, right? That's my first thought. But now I realize, wait a minute, there's also a sampling distribution around the alternative. There's an alternative box. This is called the null box. When the null is true, this is our probability model. Now we have to do, when the alternative is true, we have to do what that probability model looks like. And when the alternative is true, this is the null box. It's called the null box. And here's the alternative box for my other hypothesis. And that is that the percent of ones that she's is going to be 60%. It's going to be, this is Talia's brain, not that. Okay, so, and then the same thing, we're going to draw 100. So n is still equal to 100. And then we have to calculate a new, what's the distribution? Here's, so I showed that. So under the null, we'd expect 60%, but what are the error bars here? Well, looking at our formula up here, it looks like it's going to be the same formula except for the standard deviation here. It's going to be a little bit smaller. But it turns out the standard deviations of these 0, 1 boxes don't vary very much. Look, we have quite a big difference in our hypothesis, but especially in the middle here between what's the difference? A 50-50 split gives us a standard deviation of 0.5. What will be our standard deviation here? It will be the square root of 0.4 times 0.6, which is equal to, I don't have my calculator with, maybe I do. No, I don't. But it's very close. It's like 0.48 something. And so it's so close that we are going to say it's approximately 0.5. All right, so later on, I can show you how you do it if you wanted to. It's just going to make it a little more complicated if we use the exact, and it's very close. So we'll say we have the same, so approximately the same standard error of the sample percent equal to 5% for both of them. Okay, so now that makes it easier and more intuitive here. And so that's what we've got. And now what do we need to do? We want to calculate, our goal is to calculate the probability of a type 2 error. So here's our null cutoff of 1.65, right? And so this is our type 1. And we set that at 5%. But we want to calculate this probability here. This whole area. So that's, if Talia really does, if she really is this baby genius or really baby stat whiz, then even if I'm right, and she really is that, this test is not going to detect it that percent of the time. We're going to make we'll make that error. That's the type 2 error called beta, and that's what we want to calculate. And the percentage of times that the test would pick it up is called the power of the test. And so from here would be the power of the test, and there is the power to detect that effect size, that difference, and it would be this area. Well, it's more than 50%, but it doesn't look, it looks like there's quite a big type 2 error. So how do we calculate? Well, that involves translating the distance, this is a distance of our effect size in units, so this is d in units, the distance in units, and it's equal to a distance in z-scores times our conversion factor. So we know this right now. We know this is what? The standard error for percent, we just calculated this to be, this is 5%. Do we know z alpha? Yes, z alpha is 1.65%. So all we need to do, now these are all distances, so I'm going to put a little absolute value around this. I'm just concerned about these distances. So this is 1.65. This is z beta times 5% is going to be equal to our effect size, which is 10% right there. It's 60% minus 50%. All right, so that's our relationship, and we are going to solve for z beta. All right, and once we solve for z beta, we can use the normal table to get beta. So let's do that. So we'll solve for z beta, and we get what? 10% equals 1.65 plus the absolute value of z beta times 5%. So what do we get? We get 2 equals 1.65 plus the absolute value of z beta. So z beta equals 0.35. All right? So once we have that, z beta, the z-score is 0.35. We can figure out the probability of the type 2 error by using our table again. So we look up z equals 0.35, and we see that 27.37 is of the curve is in the middle. That's our middle area. Let's round in our head. Let's just do this in our heads. So let's round. On the homework, you're going to have to be more careful, but while we're just getting this intuition here and in class, let's just round that to 27. So we have 27 in the middle. So we just want that tail. So that's 20, so the whole thing's 100. Minus 27 is 73 for the two tails. So this tail, let's just look at it here. So we basically have the middle area is 27 between, do you see what this is? This is a 0 here. But if we were looking at this curve, this would really be z beta equal to negative 0.35, but we're just concerned with the distance. So we have between negative 0.35. I'll just dot it in so you can see what we're doing here. And z equal to 0.35. That's our middle area, is 27. Do you get it? And we just want this side. We don't, that doesn't enter in. So this is always one-sided here. And so this right here, the area of that, which is called beta, okay, so it's beta is equal to what? 100% minus 27% over 2. So that's 73% over 2%, which is 36.5%. Now, it's often written, that's as a percent, but it's often written, or it's this as a decimal, so that would be the same thing. Okay? So that's beta right there, and that looks about right. So that's 5%, and that's 36.5. That's a big type 2 error. And the power of our test, what's the power? This whole area, all this. That's the power of our test. So the power is just 100% minus beta. So the power is going to be equal to what? This is 36.5. It's 100% minus beta. So our power, we can write it here, now, that's what would be called a somewhat underpowered study, because just as there's a conventional cutoff for the type 1 error is 5% or less, well, for beta, most granting agencies, if you're planning an experiment, the typical value is 20% or less, which means typical, conventional, what you're aiming for, it's a power of 80% or more. So this would, we'd have to, this is too great a type 2 error. So you might think about, well, how are we going to get that smaller? Well, we talked about there's a trade-off. If we make that smaller, then alpha becomes bigger. So what can we do? We could say, okay, Talia, let's separate these curves out and think, boy, if only she could answer like 65% of the time, that would move this over. Imagine putting the center at 65. Oh, wow, 70 would be even better. Where am I? I've lost my 1. That's 60, 65, 70, 75, 8. Whoa, we could move her way out here. But she's really, that would be fantastic, or even further, 90%, This is 60%. Oh, I'm not, yeah. Could move her way out here, but then I could take her on tour and bring her to this class, and she could sit up here and be the professor if she was that smart. So no, it just you have to pick an alternative that corresponds to reality, and I really don't think she's much better than 60%, so I can't set it any bigger than that. So what am I going to do? Well, the best thing, the other thing is to make our test more precise, to narrow our error bars, to reduce the size of both errors by just being more precise, a more precise measuring statistic. And that would be, we can get more precision by giving her increasing n. Our standard error, if we make these standard errors smaller, we can do that by getting a bigger sample size, giving her more questions. All right, so let's just summarize that on the next page. Okay, so we're looking at the next page here, and so here's the options we just discussed. If we just change this slider back and forth, we have a trade-off between the type 1 and the type 2 errors. So here's our type, we made our type 2 error smaller by moving the cutoff this way, but we increased our type 1 error right there. So that's the problem if we change our significance level alpha, so there's a trade-off. So if alpha goes up, then beta goes down, and vice versa. All right, so how about changing the alternative? Well, that's what we just talked about. If Talia could answer that many questions, that would be great, but we probably wouldn't need a significance test. So we're constrained by reality. We have to choose an alternative hypothesis that corresponds to reality. So we really can't just separate them that way. So the last thing that we can do is we can increase n. So if n increases, then our error with a bigger sample size will go down. We'll have a more precise measuring device that can give us better evidence of each hypothesis. Okay? So we'll have, and you can see that because if we increase n, look what happens. The standard error is equal to, the standard error formula is equal to SD over root n, right? If you want to change it to a percent, then you multiply it by 100, but the bigger the sample size, the smaller the standard error. So this is what we're going to do. So this is what we're going to do, and so let's do that with Talia. So let's go to the next page, page 7, and let's keep everything the same and just increase our sample size, which means I'm going to ask her 400 questions. Let's just do that to 400 and see what happens. I mean, as you can see, when you have a bigger sample size, it's a lot more trouble to do a big experiment, and that's going to take a long time to ask her 400 questions. But let's see what the power of the test would be then. Will that decrease the probability of a type 2 error? Yes. By what factor? Well, if n increases by what? Times 4 from what? 100 to 400? Let's think about it. If we change everything, we're just going to change these error bars here. And so if we multiply n by 4, then we're going to reduce the error by the square root of 4, which is 2. So if n goes up by 4, then the standard error will go down by square root of 4. So we know what's going to happen. It's going to go down from what? From 5% to half that. So we have to quadruple our sample size and ask poor Talia 400 questions and poor me to just have our error. Okay, so here's our basic formula again, and here's our new picture, etc. Okay, so let's just draw in our new picture here. So here is still our null hypothesis, and here's our alternative hypothesis, okay? And now it's still 50 and 60. That's no different. We haven't changed that. We're keeping everything the same. It's just that now, instead of it was easier for me to draw it on a different scale here, rather than, it's the same thing rather than squashing this down. Okay, so now we have 50%, right? This is a 0 here. And instead of going up to 55, this is going to be 52.5. This will be 55, 57.5. And you see how now we have 1, 2, 3, 4. Wow. If we stick with this is 4 standard errors here. Well, we're going to figure that out here, but look at that. You can just see it. Okay, so we'll use the same formula here. All right, and you can see that, look at the errors here. They're going to be much smaller. There's much less overlap. So let's use our formula. So all we're doing is d as a distance is equal to d as a z-score times our standard error, right? So we know this distance is still 10%. And here, we're measuring this distance between the null. Boy, I don't think I talked about that last time. We'll talk about it. This right here, the null cutoff divides the distance in z-scores into two pieces, z alpha and z beta. We'll talk about that in a minute. So our formula says z alpha plus z beta times 2.5%. Now, is the alpha still 1.65? Yes, we're still going to set it at 1.65, so let's put that in. So here's 1, 2, 3, 4. So let's draw in 1.65. This is z alpha equal to 1.65. So this is still at 5%. We're keeping that the same. We're going to have a much smaller type 2 error. So we're keeping everything the same. So our probability is still right here, 5%. And now we want to calculate this tiny little probability. Okay, so let's do that. So we have 10 divided by 2.4. This is 4 right here. 4 is equal to 1.65 plus, these are both absolute values, sorry, plus the absolute value of z beta. So the absolute value of z beta is equal to what? It's equal to 2.35. It's a much bigger z-score. So now let's see how, what I was saying was this null cutoff divides the distance of this distance. Here, let me show you what I'm doing here. So we'll go like this and this. So this is a 10% distance, right? But it's 4 in z-scores. And this distance is 1.65. This is our z alpha. And this distance is 2.35. And that is z beta. And you can see it's basically, if from the alternatives point of view, you'd have a z-score of 0 in the middle, 0, and this would be negative 2.35. So to find that little probability, and you see how this cutoff divides the distance in z-scores into two pieces. And now we set this to be the same, but we just made our standard errors, we made it so much smaller that now the distance between 50 and 60 is 4 standard error. Okay? So now look what we're doing. So we just want to find, you can look this up. This will be our middle area between 2.35 and 1, 2. This is really negative, but that's why I'm doing the absolute value here. And positive 2.35. We'll find that middle area, and that little piece will be the tail. So let's just go to the back of the book, and let's just do that. And so our 2.35 is going to, let's see, 2.35. So it's about 90. It's 98.12. So about, let's just say about 98% between there. So this is 98% in the middle. Okay. So then the tail would be what? So the middle area, and you're going to have to be more precise in your homework, equals 98% approximately. So beta equals, just the left-hand tail here, equals 100 minus 98 over 2, which is 1%. So beta, our probability of this tiny. So power, the power to detect the power to detect that difference when it exists is, we're going to have a very powerful test, is 100% minus 1%, which is a 99% power. That's a very overpowered test. So I could be, what we're going to do next is we're going to say, okay, to get 80% power, the conventional cutoff, how big a sample size? How many questions do I need to give Talia? And we're going to use the same relationship here, but then we'll know Z alpha and Z beta, and we'll solve for the standard error. We'll solve for n and the standard error. So if you want to look at the summary here for where we're going on page at the end of the chapter on page 11, let's look at the summary. Power calculations, what we've done, it's the same formula. I keep forgetting to write this as a distance. It's the same formula, but to calculate beta for a given sample size, a set alpha, and you set your particular alternative, you solve for Z beta here, and then look up beta, right? But when we want to calculate n, we're not going to have, to calculate n, we're going to have a given alpha. The conventional levels would be alpha equals 5%, beta would be 20% for a power of 80%, right? We want an 80% power. And then we'd have to pick a particular alternative. And then, you know, we substitute, we'll get the correct standard error, and we'll solve for n. We'll get a standard error from that, and then we'll solve for n. So that's what's coming up next time. See you then. That will be on Tuesday. Bye.